In this video, I'm going to give some background to Joseph Fourier, the French mathematician and physicist, and then I'm also going to focus on Fourier analysis, the thing that he's most famous for. So he was born in Auxerre, which is sort of southeast of Paris, so fairly central France. He was born there in 1768, so his lifespan is around the time of the French Revolution and then Napoleonic times. And this featured large in his life. I mean, he was the son of a tailor, but he was orphaned when he was age 9, and then he was educated by the monks, essentially Benedictines. He then joined the army. I mean, he was prominent in his local area in France, promoting the French Revolution, and then he served in the army under Napoleon. I mean, when Napoleon had his Egypt expedition in 1798, Fourier was one of his scientific advisors, and he returned from Egypt with the intention of having an academic career, but Napoleon had other ideas and appointed him a government official, and he sort of got tied up in doing all of overseeing civil projects and things like that. But he did manage to continue his discoveries, particularly in heat flow. That was his big thing. And he ended up being one of the 72 names on the Eiffel Tower, along with a lot of the other scientists of that time. So he, as I say, I mean, he was looking at heat flow. He was actually the first person who's been credited with a description of the greenhouse effect, because he was looking at, well, what temperature would we expect the Earth to be based on the energy coming in from the sun and the distance of the Earth and all of this sort of thing. And he calculated really that the Earth should be a lot cooler than it is. So he was then saying, well, there must be something in the atmosphere that's warming the Earth up. There must be some kind of heat trapping mechanism going on with the atmosphere. He didn't call it the greenhouse effect, but the way he was describing this insulating effect of the atmosphere, essentially it was the same sort of thing. And then he was looking at heat flow in general, and particularly conduction. He came up with an equation for conduction that is still used. And then while looking at these this sort of wave transfer of things and looking at heat flows, he then came up with the idea of Fourier series and Fourier analysis, where you can then look at periodic functions that you can see they're periodic, but they're very complicated, and then analyze them in a certain way in order to write them as a sum of trigonometric series. So say, for argument's sake, you had, the one they always like using is a guitar string or something like that. So you're playing the guitar. You might get, if you were plotting out something which was, say, you've got amplitude against time. So we're just drawing out essentially our wave form of the guitar string. So you might get something which is, I don't know, it might be a complicated shape. I don't know, say you had something like that, but you can see it's repeating in some fashion. So you've got this periodic nature, but you can't just say, oh, well, here's what the function is, here's how we're going to describe that wave. It's too complicated to easily write out in a mathematical form. So what Fourier showed was actually you can write any periodic function as a collection of sine waves. So if you've got some a sine, if you write it in a really generalized form, you can have a whole load of these trig functions, and you just add them up with different, keep changing all these constants and such like. Well, let's even put another one on the end to put in all of our main transformations of a sine wave. If you add all of these up, then you can create this function. This was the idea. And then you can start looking at the frequency of these individual functions. So this would be like the harmonics, when we're looking at stationary waves. So we set up a string. Now, usually when we're looking at our stationary waves, we'll go through our harmonics and say, okay, well, we've got that one, and then we'll have that one, and we draw these out all one at a time. But when you pluck a string, you don't just get one harmonic happening. This is going to be, if this was our guitar string playing a particular note, it's going to be a combination of these harmonics. So you can do the Fourier analysis and then plot out again an amplitude against frequency graph, and it might come out, I don't know, something like this or something, where you're then seeing the different harmonics. So these will quite often be fairly evenly or actually evenly spaced. You might get, these are going to be the frequencies of each one of these. The harmonics build up in a sequence, quite a logical sequence where they're all multiples of each other, which is why you're going to get these constant gaps quite often in these spikes. So this will then show you, well, these are the frequencies which are combined in order to create this final note. So you've got this two-way process with Fourier analysis where you can say, right, well, here's a note, let's pull it all apart and then see what frequencies, what harmonics it's comprised of. Or you can go the other way and say, well, if we add all of these harmonics, what note would it make? So you can go in both directions with this analysis, and it just makes it gives you a possibility to mathematically describe it more easily and to see what's actually going on inside these, something as complicated as a note on a string, or you see it with crystal structures. If you're doing crystallography, so if you're doing some X-ray diffraction or something, you've got a crystal which is it's got certain gaps between the layers, the structure of the crystal. You fire these X-rays at it. Now, you're choosing X-rays because remember, diffraction, you're getting the biggest diffracting effect when the gap that the wave is going through is similar to the wavelength of the wave. So it happens to be X-rays for most of these crystals. So you're going to get this diffraction pattern that comes out. Now, the diffraction pattern is not going to be simple. It's going to be composed of lots of different components based on the different spacings of the atoms in the crystal. So you can get a complicated diffraction pattern that'll look something like that. You run it through your Fourier and it will give you the breakdown of the structure inside the crystal. So again, it's a similar process of how you're finding a combination of underlying structure, how that combines to give an overall effect. It's used in sonar because you can do a similar thing. You might get a sonar pattern if you've got a submarine that's letting off a particular noise. You can then go about classifying the particular submarine it is, because you're going to get a signal. The signal is going to be made up of the machinery in the submarine. So a certain engine will have a certain signature. And you can put all of those bits together, the different machinery noises in the signal, in order to try and classify the target. So we've got the same thing going on there. Lots of different components grouped together to create a whole. And the Fourier analysis goes between all the individual components and the whole. The same thing again. It's actually used in JPEG files, the image files that are pretty common. So, that chops an image. You get an image, you chop it into lots of squares, like sort of pixelating it. Then each square you can split into components, to do with color and intensity and such like. So you can split that up using Fourier analysis, remove all of the weak stuff, but then you can store each of the individual Fourier profiles. So it's a lot easier to store that information. Once you've broken it into the components, you take your overall signal, break it into those components, get rid of the weak components, and then you've got simple descriptions of the strong components. You can store those, and then when you want to put the image back together again, you just take those and run them through your Fourier in the opposite direction, and you put the image back together. Okay, you've lost some of the really fine structure, but for the most part, that doesn't really matter, particularly if your intention is to have a low, it doesn't take up much space, does it? A JPEG file, it's not like a bitmap or something like that. These are, low storage, they take up a lot less memory. That was the word I was trying to look for, low memory files. So yeah, there's a lot of different uses you can have with Fourier analysis. So that's why it's so useful and comes up. It's typically a first year undergraduate topic if you're doing physics or a variant of physics at university. It will come up in your first year, optics. And most of it is done by computers, but you'll want to learn the underlying theory of how it's all put together. But that gives you a basic flavour of everything that's going on. And the person who opened the door to all of that, Joseph Fourier. So another useful person to know about.